information. Okay, so we're going to get started now. So today we're talking about cache lab and caches, unsurprisingly. So you're going to have to use some pointers now. You can see, so here's a nice little XKCD comic about pointers, if you haven't seen this one. Okay, but yeah, so we're going to talk about caches, how memory is organized in computers, the different types of locality and organization associated with caches, how they're implemented, how they work, and then we'll talk about cache lab in particular, where you will be exploring these ideas. So cache lab is due Thursday, so hopefully you have at least started it, looked at it. If not, you should start it now because it is due very soon. And also we have an exam coming up. So after cache lab, you will not have another homework, another lab due until after your exam, but you should start studying for the exam as soon as possible. We have uploaded old exam questions to the website. There's tons of them. Going through those is a really, really great way to study for the exam. If you can do all of the old questions on the website, then you are probably well prepared for what you'll see on the actual exam. Any questions about the upcoming exam before we go into caches? None? Okay. So the memory on a computer is organized into this hierarchy. So we would love to be able to, have everything be right there for us in our registers, because what a piece of code is actually able to access quickly, which you've seen in Attack Lab and Bomb Lab, you've got these 16 registers, and those are really fast. They're right there, but there's only 16 of them, and we can't have arbitrarily many because there's only so much space. And then we have the main memory. And you saw that, you would see like parentheses around RBX, which means use this as a memory address and go to that location in main memory and, get the value stored there and use that in my program. And that's a bit slower, but we have that too. The problem is it's actually more than just a bit slower. It's a lot slower than registers. So there's actually, in between these, other levels of a memory hierarchy. And you never actually in the assembly code know that these are there. They just work. The address you work with in your assembly code is an abstraction, and these will figure out how to make things faster if they can. But essentially the issue is there's a trade-off. There's a trade-off between having more memory and having fast memory. And the faster we make the memory, the less of it we're going to have. And the slower we make it, the more we're able to have. And then also going along with that, the faster memory is more expensive. It's more expensive to produce in terms of actual, in terms of cost. So this is sort of an outline of the memory hierarchy that we have on computers. So at the very top we have our registers. We've got our 16 registers that we've seen. They're really fast, like they're instant access. The code has access to them as soon as it needs them, but you only have 16 64-bit words worth of space. That's all you get. That's not very much. We want more than that. And then there's the main memory down here, which we've also, sort of seen through those addresses. And you can have lots of that. Typical computers these days will have, like somewhere between like 4 and 16 gigabytes on like a brand new desktop computer. That's a lot, but it's a lot slower. And so what we do is we put some levels of cache between. And so each level is just going to access the stuff from the level below it. So if something's not in your register and you need to get it, it's first going to check if it's in the level 1 cache. If it's not in the level 1 cache, we'll check if it's in the level 2 cache. If it's not there, we'll check if it's in the main memory. If it's not there, it might have to go all the way to your hard disk and load it up from there. And then there's also stuff even below the level of the hard disk, and that would be like if you're accessing a web page, then now you have to go over the network connection. And that's even slower than hard disk, but of course, the number of bytes you can access through the internet is significantly larger than the number you can store on your hard disk. So it forms sort of this pyramid, each level getting from the next. So we'll talk sort of about these different levels. So, right, so you saw in here, there's this difference between like the level 1 and level 2 cache, and now computers even have level 3 cache. And the main memory in that they have different types of RAM. These caches were called SRAM, and the main memory was called DRAM. So these are actually two different designs of what the hardware looks like. So SRAM is faster. It is a different type of circuitry that is able to be accessed more quickly, and it's more stable. But the cost is that it actually takes 6 transistors to implement 1 bit of SRAM memory, whereas it only takes 1 transistor to implement a bit of DRAM memory. And what this means is that we're limited in the amount of SRAM we can have because it is more expensive to put into our computers and takes up more space. So for our large storage, the main memory, we use DRAM, even though it's slower to access because it's much easier to have it in bulk. And then the smaller caches use SRAM because it is cheaper to add, or cheaper in terms of performance costs, but more expensive in terms of power use and space use and cost, monetary cost. So we have these two different types, and sort of our smaller ones use the better one, and our bigger ones use the cheaper one. Does that make sense? And there's details about these two types of memories in the book. Those aren't hugely important for this class. So when we're accessing stuff from memory, there's a property that makes caches actually useful called locality. This is the whole reason why actually having caches is a useful thing to have at all. And the idea is that when we access data, it's probably going to be the case that we are either going to access that same data again sometime in the near future, or maybe we'll be accessing data that was stored nearby in memory sometime in the near future. So these are two different types of locality, and they're named temporal locality and spatial locality. So temporal locality is then the accessing the same data again sometime in the near future, and spatial locality is accessing the data nearby in the near future. And so the idea is with these caches, they're storing a subset of memory, a subset of the larger bit of memory. And if we load up the stuff that we're using, it's likely that the next time we make a memory access, it could be that same thing that we just loaded up, in which case it'll be in our cache, and we don't have to go all the way to memory again. Or it might be the case that it's something right next to it. And so if we load up, if we load up a block of memory every time we put something into our cache, then we can possibly get this stuff nearby that might be accessed soon after too. And this is why caches work. If our accesses were just completely random and we had no way of predicting what would happen, well then we're probably going to have to go to main memory every time, and the cache isn't going to help us very much. But the fact that we're going to be accessing the same stuff over and over means that if we load it up to a faster piece of memory once, then we can access it just from there. And when we need it, it'll be right here in our cache rather than going all the main memory until that's no longer something we're using, and then we load up something else to replace it. But then we might access that multiple times. So does that make sense? How locality is the reason why caches can be effective? Okay. So how do caches work? So how do we actually load things into them? So we have 64-bit addresses for our memory locations that we're trying to access. What we do, the way caches are implemented is we sort of divide these up. We divide up the address and partition its bits into 3 meaningful parts. And these parts are a tag, a set index, and a block offset. And the exact sizes of how many bits go into each of these depends on the implementation of the cache. And so in Cache Lab, you'll be implementing a cache simulator that takes in how many bits go into each of these 3 bits as its parameters, and simulates a cache with that design. but we partition the address. So the address is 64 bits, and we sort of say the first however many are the tag, the next however many are the set index, and the least significant however many are the block offset. And this is how we're going to look stuff up in our cache. So the way a cache is organized is we end up with a bunch of sets. So sort of draw the picture like it's drawn in the book. We have a bunch of sets. This is set 1, set 2, all the way down to set however many sets we have. And then each set has lines in it. So each set has the same number of lines. Let's just draw with like 2 lines. And each line contains a couple things. So these will sort of be the lines of the set. So this is like if e equals 2. So we have 2 to the s total sets, where s is the number of bits in the set index. Because of course we can index 2 to the s different things if we have s binary bits. So then each set has some number of lines. In this case, this example is 2. And then what the lines store, they store a few different things. They store a valid bit. They store tags. And then they store a bunch of blocks, or a block of memory. And the size of this is 2 to the b bytes, where b is the number of bits in your block offset portion of this indexing scheme. So we have this picture of the cache. How do we actually look stuff up in it? So what we want to do, here's a PowerPoint example of this. So what we want to do when we have an address, we have some address, and it's broken up. We have some address. Can everyone see when I'm over here? So we have some address, and we've broken it up into its tag, its set, and its block parts. And we want to look it up in our cache and see if it's in there. See if we can just read it out of the cache, or if we have to go to main memory for this. So what do we do? So the first thing we do, so we have these set bits. What these set bits tell us is they're an index into one of these sets. We read it off as an unsigned number. Maybe our set bits are 00010 or something. Then what we would do is say, okay, that's the number 2. We should check set 2. And then what we do is we say, okay, now we have this tag. We want to see if there is something. These have the valid and the tag too. We want to see, is there a line in this set that has the same tag as this piece of memory that is also valid? So we look through, and in this case, there's more than one. So there's a couple we have to check. But we can check, is the valid bit equal to 1? And if it is does the tag match? Maybe this one doesn't, so we'd have to come and check the next one. It says the valid bit equal to 1, and does the tag match? And maybe this one does. So that means we have found this address in our cache, and now we just need to look it up in here. So then the last thing that we get is this block gives us an index into this chunk of memory. This is where the actual stuff is being stored. These are sort of just indexing information. The set, the tag, the valid is just keeping track of what's valid and what's indexed. It's sort of a really, really simple hash function is what it is. It's a hash function where you get it straight from the bits. And then the block will tell us where in this block, it tells us the index where we can read off our actual word that we're trying to look up. Yeah?
So the valid bit and the matching the tag bits is all you need to determine if it's a hit or a miss. Like the block index doesn't really matter.
Yeah, so the block index, these blocks are big enough to hold all of the indices in here. That's how we determine this by how many bits we have in that section, so it will be able to index all of those. So all we need is the tag and the valid to know if we actually hit it or not. Okay. So does this sort of picture of a cache make sense? And if we came in here, and we looked up the correct set and none of the tags matched, or the valid bit was 0, because if the valid bit is 0, we don't care what the tag is. That's our way of indicating that it's junk that hasn't been filled up with the proper memory yet, because maybe our cache we've just started and the cache is empty. All of the valid bits start as 0. If it's not in here, then what we have to do is we have to then go to main memory and look this up. And then we can put it in our cache so that the next time we look it up, hopefully it'll still be there. Right, so the idea here is that we have the cache is a smaller piece of memory than whatever it's accessing. It's smaller than whatever is one level below it in the hierarchy. So what we do is we just keep a subset of usually the most recently used blocks that we've accessed from that larger piece of memory. And so there's, we could, if we wanted, implement a cache. This scheme, we had a very precise way of figuring out exactly where, something belonged. We could just have, something along the lines of, as long as our cache has space, whenever we access something, we put it in the cache and sort of keep track of where it is with some scheme where we never actually take anything out until it's completely full. And sort of this, if you look at this, you'll see, well, if we always have like the same tag and set, well, then we'll keep accessing that same line even if the other ones are untouched. The difference between these two is that this is a very fast way to get at something. This is a very fast way to figure out where in the cache it is versus just always put it in unless until there's no more space, and then keep track of where it is, which is somewhat arbitrary. The sort of always put it in, keep track of where it is scheme is what would be used by, say, the hard disk level of the hierarchy. So your hard disk, it doesn't, sort of look at the data and figure out where to put it on the hard disk based on what you're actually writing to disk. As long as you have disk space, it's going to put it on the disk, and the file system keeps track of where it is for you, so that when you ask for it, it can find it. And you're not going to, you're not going to read a web page from the internet and accidentally overwrite the other web page that you read before it because they happen to, have the same bit pattern in the wrong place. You will only overwrite stuff if you've, filled up your entire hard disk. But for a higher level cache, so like the level 1, that is sort of a slow scheme to be manually keeping track of where everything is. So this much faster sort of extremely simple hash function technique allows us to figure out where in the cache something will be very quickly, and we might, as a result, overwrite it even when there is theoretically other space in the cache that it could go into. So this is a distinction that sort of parallels the distinction between the larger pieces of memory and the smaller pieces of memory. We want the smaller things to be faster. So here's an example of a miss. So let's see. So we're requesting block 12. I guess we're requesting it from this picture here. So we're going to request block 12 from this cache. It has 4, 9, 10, and 3 in it. And that none of those are 12. So we missed. It wasn't in our cache. When we went to look in our cache, it wasn't there. So what we're doing is we're going to go down to memory. We're going to grab block 12. And then we're going to put it in the cache so that if we ask for it again, it will still be there right away the next time. And so we can have a couple different placement policies for how this works, how we determine which gets evicted. So a common thing to do, if we don't have a scheme like, if we have multiple lines that we can put it in, because these all have the same set and tag bit, the most common is just sort of the least recently used thing in the set of things that we're potentially evicting is the one that we evict. whatever has been the longest since we've accessed, because that's the least likely that we'll access it again in the near future. You could also just replace at random. That's a different replacement policy. In practice, that usually is not as good. Yes?
How do you calculate what's the least?
Right. So in order to calculate what's the least recently used, now we also need to be keeping track somewhere of some sort of how recent has it been used. And there's a couple of different ways to do that. You could do it with a queue, because just have a queue of all of the things that are batched together, or a queue of all of the things in the set of when they were put in, and then sort of when you add it to the cache, you put it at the end of the queue, and when it comes time to evict things, you evict the thing that's at the top of the queue, at the head. You could also sort of just keep a timestamp on everything, and then when you need to evict things, you just check for the one with the the oldest timestamp. Either way works, and you'll get to make the decision of which one you want to do for Cache Lab, because you'll be implementing a cache simulator that simulates a least recently used eviction policy. Okay, so there's a couple different kinds of misses. We categorize the misses into different classes based on why the miss occurred. So initially, when we start our computer up, the caches are empty. They don't save anything from over time. It's RAM that gets reset when you turn it off. And so you start up a program and there's nothing in the cache. Anything you load at that point is going to miss, guaranteed, because your cache is empty. So the first access is always going to be a miss. The first time we access any piece of memory is going to be a miss. We can never have, unless it's been loaded up in a block because it's nearby, something that we already loaded. But the first one, at the very least, has to be a miss. We might also, we have the situation where we go to load something up, and it conflicts with something that's already here. So we load it up and it has the same tag and set as maybe set as over here, and both of these are already full. So we've missed because it's not one of the ones in here. And even if this set is empty, we're still going to have to replace with this with this particular scheme of how we're going to get stuff out of our cache. Or we could, actually be at the situation where the cache is completely full and we've asked for something that's not in it. There, no matter what our cache management policy is, we're always going to miss. Because, of course, there's no way it can be in there. It's not in there and we're going to have to replace something. So, this middle one, the conflict miss, that's one where really your, how you get stuff out of the cache affects, if a certain data access pattern is going to have a high miss rate. Okay. So, any questions about caches so far? None? Okay. So Cache Lab, you're going to implement some of this. So the first thing you're going to implement is a cache simulator. So essentially, you're going to take this scheme of how to divide things up into sets, and have tags and valid bits and blocks, and then you'll write a simulator that, given a pattern of memory accesses, will tell you how many times it goes to look up something and it misses, and how many times it goes to look up something and it hits, and that sort of stuff. And so an important thing to note, because some people are confused about this sometimes, is that you're not actually writing like a cache. You're not actually storing any of this memory. You're just simulating the behavior of how many hits and misses would you get. What would be the patterns if you actually had this cache. And of course, it wouldn't make sense to actually implement a cache, because you're writing a program that's using the actual cache. So it's sort of like it would never actually be a useful cache in the sense that the actual cache is a useful cache, because it's storing stuff in memory, which then has to go through the cache itself. So you're not actually writing the cache. You're just simulating its behavior. As was pointed out, because we're just simulating it, sort of this block offset doesn't matter. We know that that's going to be there. Not the offset matters. The actual value in here doesn't matter. We know that there's space for it in this chunk of memory that's stored in the line of the cache. Since we're not actually using the actual memory addresses, we're not actually storing the data, we don't have to do that lookup. So essentially, we're ignoring what those bits are. Whatever they are, it indexes into here, and there would be something there. But we can determine the hit or the miss from just the tag, the set, the valid bit. So we don't need to care about those bits. We're just counting hits, misses, evictions. That's all we're doing. So you will be implementing this cache simulator to work for different number of set bits, number of block bits, number of lines per set. And those are parameters that are passed in to the program. So it's something, your however you write it has to handle, it has to handle whatever inputs it's given and do the correct thing for those ones on that run. And you're required to use the least recently used eviction policy, replacement policy. So, if you want to implement that with queues, if you want to implement it with timestamps, if you want to come up with some other way of keeping track of that, that's up to you. But whatever it is, it needs to accurately evict whatever is the most recently used thing in that set. So a cache is an array of lines. Essentially, you have the set, and then in each set you have some number of lines, and then that indexes into one of these, this thing. So that might be something in terms of actually implementing it, that you want to sort of have a 2D array indexed by the set and by the line, and then you can iterate over all the lines in a set. And if that's something you need to do, you can get at a particular one and update the information you're storing about it. S, capital S here being 2 to the number of set bits, E being the number of lines. There's a special name. I guess it wasn't in the slides. A special case of caches is where you have exactly one line per set. And that means that you only have to look at the valid bit and tag for exactly one thing. That's called a direct map cache. So we can, just by looking at set tag, there's exactly one place where it might be. If it's not there, we evict it. We don't have a whole set of things at each space. And then if we have only one set, and then all of the lines are in one big set, that's called a fully associative cache. Direct map caches are used in implementation more than fully associative ones. They are faster, even though they might produce more misses due to conflicts.
One of those two are we building?
So you're making one that could be either, because you're going to take in E as one of your parameters. So if E is set, if as E and S are both parameters, if S is set to be only 1, then you're simulating a fully associative. If E is set to be 1, then you're simulating a direct map, or you might be simulating something in between, where you have not a greater than 1 sets and greater than 1 lines per set. So each cache line, you need to keep track of this valid bit, a tag. You don't actually need to store anything for this blocks, because that's where the memory is stored by the cache, which you're not actually worrying about. And you need to be able to store some sort of information about what the least recently used thing is, so that you can use that. Yeah.
Since E is associativity,
Mm-hmm.
fancy way of saying line.
Yeah. So the fancy term we give to number of lines per set is associativity. Yeah. It's not terrible terminology. Yeah. Okay. So one of the things you will find useful in your cache lab is getopt. So getopt is a program, or a function as part of the standard library. If you'll include this header file, you'll have access to it. And it is very useful, because what it'll allow you to do is it allows you to get arguments off of the command line without writing all of the boring logic for that yourself. So you should read the man page about that to see how it works. So if we just man getopt, then we get information about it. I think, so that was not the function. So man, if you don't get, when you do man get opt, what you saw is that I got one for an actual program called get opt, but what I really wanted was the standard library function. So to get a standard library function, it's man3. And this tells us all about what get opt takes. It's arguments. It tells us how to use it. It has an example at the bottom, which is really useful. So this is what you should read if you want to learn more about get opt. You should probably be doing this on the Shark machines. As always, it's the best way to do it. Now get opt, it takes a switch, and that switch will go through your different options and tell you what to do with them. Here's an example of it. So this one, it's telling us we've got two options, x and y, and we're going to turn these into integers and store them in x and y, and then our program has access to them that way. And it's saying these colons mean that they're both required. But you can read the documentation for the details on that. You're essentially, you'll be doing the same thing as like in these examples. You'll sort of just copy it over as necessary for your programs. Another thing that you might find useful is fscanf. So fscanf can read from a file, and it will allow you to get stuff out of it with the different, the different designators, the %d and %x, and all those that you would use, same as in printf, to get values out of a stream. So you can, in the same way that we did man on get opt, we can man f scanf, and it will tell us all about how to use it. This will be useful for being able to get your, you have a file that's telling you what the cache should be doing. It should, access this address, access that address, write to this address, write to that address. And, this will be the way that you get that information into your program so that your cache simulator can use it. Yes?
Quick question. How do percent character? Will the first one get the space? If it's like space C?
If it's space C,
And then
yes.
okay, so
Yeah.
first.
Let's see, okay. What else? Here's an example of that scanf being used. So yeah, so here it expects a string that starts with a space and then has a character and then a space, and then some hex value, a comma, and then it's going to read the last thing off as an integer. This is essentially the sort of thing that you're going to use. This is about exactly what you'll want to be able to read the trace files. You'll need to be using malloc to implement, to allocate memory. You don't know how much memory you'll need for your cache because, of course, the size of things are passed in at runtime. So you'll be able to get the memory at runtime with malloc. And remember the warnings we gave last week about freeing everything you use and initializing memory before you use it and such. So then, after you have implemented this great cache simulator, you're going to use it to test out how efficient you can write matrix transpose. So of course, matrix transpose is the very simple problem of we have a matrix and it's got stuff in it, A, B, C, D, and we want to transpose it. So that means we want it to become A, B, C, D. So essentially, we're sort of mirroring it over the diagonal. Rows and columns are flipping. So, of course, we want to be able to implement this fast because fast is better, right? How do we optimize this so that it has good cache behavior? Because now that we know about how things are looked up in the cache, this is a bunch of values stored in memory, and as we go through them, it's going to look them up. How do we make it so that we can optimize the number of times we go to look up, say we want to look up this 10, we want it to be there in the cache, if it's possible for it to be there. We don't want it to have been evicted by something else. So here we're supposing that our block size over here is 8 bytes. And these are 4-byte integers. And so we access 0, 0. This 1 is a miss. Nothing's in our cache yet. It's the first access. Okay, so then we access B00 because we're moving A00 to B00. It's the first step of the transpose. It's a miss because we haven't accessed this address yet either. Now we're going to access A01. So we get this 2. And that's a hit because we had already loaded this up into the cache. This is a block of our cache here because it's 8 bytes, so it can fit 2 of these things. We loaded it up. When we loaded the 1, it loaded the 2 with it. And then we go and we put it over here. So we put B10, we set it to 2. And this is a different block of the cache than the 1 was in, because the 2 is not adjacent to the 1 in memory, because now this is the transposed matrix. So since the memory is stored in by the rows, this isn't adjacent anymore. So now that's a different block. So what should we do next? The question is, should we load up 3 and 4, or should we load up 5 and 6? Does anyone have an idea as to which would be better?
Load 5 and 6.
5 and 6. So why should we load 5 and 6? That's right.
So in matrix B, 5 and 6 will end up in the already loaded blocks.
Right, yeah. So, our naive algorithm, like if we were doing transpose by hand, we'd probably just go on to 3 and 4 next, because, we're just going to go across all the rows and put them in the columns. But our cache, the way it's implemented is we've already loaded up these cache blocks, the 1 for 1 and 2. And these cache blocks are going to be the ones that contain 5 and 6 in our transpose. 5 is going to go here next to the 1, and 6 is going to go next to the 2. So if we do 5 and 6 next, what that means is if these are already loaded, we won't have a miss when we go to put them in the cache, when we go to write them to matrix B. And that's good. If we go on to 3 and 4, well, then we're going to be loading up more stuff down here. And if we evict one of these before we come back around to 5 and 6, we have to load them for the 1, and then we have to load them again for the 5. And that means we did a load for each of these. If we can get away with only loading it once and filling it up with the stuff that's going to be in it before we evict it with something else, then we've improved our cache performance, and that's going to make our program run faster. Does that make sense? So this, what we've done is we've done what's called blocking. We're transposing 1, 2, 5, 6 first, and then maybe we'll do 3, 4, 7, 8, and then 9, 10, 13, 14, 11, 12, 15, 16. We've sort of divided our matrix into blocks, and we're conserving it 1 block at a time. Because if we look at what's happening to the caches, we see that improves cache performance. So, that right here, that's where it says blocking. We're dividing into submatrices. And the best submatrix size is going to depend on the details of your cache, and it's going to depend on the details of your matrix.
So the 1, 2, 5, 6, that worked really well, but if you were to block over the 3, 4, 7, 8, and if you were transposing it, would that still...
Okay, so let's think about what blocks these are going to be in. So 3, 4. So 3, 4 is going to be another block right here together. These are 2 adjacent things. And 7, 8 are going to be a different block that are right next to each other. In our matrix, in our transpose matrix, these are going to end up down here as 3 here, 4 down below it, and then 7 here and 8 below it. So we'll end up with the same thing where if we miss when we load up for the 3 and 7, or the 3 and the 4 in B, but then those 2 spots are there for us to put in the 4 and the 8. Does that make sense? Okay. And depending on how quickly these things will be evicted and how many bytes we have in our cache block, we might be able to increase the block size and get better performance from that. If this was more than 2, then maybe we'd want to consider something bigger than a 2 by 2. So this is one of the strategies that will be very helpful for you in Part B of Cache Lab. So we have an example where we're doing it here. Did you see this one in class of matrix multiplication with blocking? Okay. Did everyone? How did you feel about it? Did you understand it? Was it confusing? Confusing? Okay. Let's definitely go through it again then. So, the way you multiply a matrix, two matrices, is that the value at index ij of the product is all of the things in row I of the first matrix multiplied by the things in j of the second matrix. You do the dot product of row I and column j to get element ij of the product. So we want to make this faster. So we're assuming here that we're multiplying matrices of doubles, so they're 8 bytes. And we're saying that the cache block is big enough to hold 8 of these. And then the cache is going to be much smaller than the matrices. We're going to assume that it's going to just overwrite stuff. We don't have nearly enough space to just load the whole thing up. So the first iteration, we want to know, how many misses are we going to get when we calculate this. So what we do, so we have this line of matrix A, the first row. And so every time we load up the first one, our cache block is 8 doubles, so that's going to load up the first 8 things in this row. And then when we get to the 9th thing, we miss again, but it loads up the next 8. And then when we get to the 17th thing, it misses again, but it loads up the next 8. So in order to load up this row, we're going to have n over 8 misses. Does that make sense? Or n is the length of the row. Because each first member of each group of 8 is a miss, and then it loads up the rest, so they're there when we go to access them. And then when we go to do this column, well now, since we load up the first 8 of this row, when we load up the first element, the element in this corner, then that's a miss. And then we come down to the next one, and it's not there. It's not there. Our matrix is much wider than 8. So what we end up doing is we miss every single time we access the first element of that row. So every single element of this column is a miss, so that's n more misses to give us 9n divided by 8 misses total. Does that make sense so far? I would calculate that. And so then afterwards in the cache, what do we have loaded up? We have the last 8 elements of the first matrix are in our cache. And we have this 8 by 8 block from these 8 rows that we loaded up, and then the stuff over here that we didn't use, going 8 wide. So does everyone see how we get that in our cache when we're done? No? No, so the assumption we're making here, of course, is that our cache is much smaller, so things are being overwritten. If we had a huge cache, then maybe all of this could still be in it. But we're assuming that our cache is just going to keep overwriting. The best we can do, if we have a really bad cache, is that this would be in there, and these 8 would be in there. Okay, so then we go again. We go again, and what happens? We do the same thing to the first row, and if we've overwritten the beginning of it, then we have to load that up again, and we load it up again, and we load it up again. And we're going to have n over 8 misses again because we evicted the beginning of this first row. And then, once we start loading these up again, eventually we'll evict the end. And so then we have to load it up again too. And so we're going to have n over 8 misses again. And then we do the same thing over here. We have a miss every single time we access a new row. And in doing that, we're evicting this bottom block. And so by the time we come back down to it, it's been evicted, and we have to load it up again. And then we end up with n over 8 plus n misses again. Because we essentially threw away all of this stuff before we used it. And we threw away this before we used it again. And so we look, we're going to do this n squared times, because there's n squared things in our matrix. And that's going to give us 9 over 8 times n cubed misses, which is polynomial, but this isn't an algorithms class, so that's not good enough. So the solution is we want to block it up. So we want to sort of say, if we look at just a block in C, then it's sort of that block carried across the rows and that block carried across the columns of A and B, and we can get those into C. Actually, I'm not sure what this plus C is doing here. Is that right? Because that's what we're calculating. I don't think this is supposed to be here. Unless someone else sees why. So what?
There's something you're asking on.
So C is what we're trying to calculate. We're trying to calculate C as the product of A and B.
Yeah.
So
Just empty.
yeah, okay. So yeah, the idea is that we're taking these blocks in the rows of A and the blocks as the columns of J. And what we're going to do is we're going to calculate the product of everything in a block before we move on and calculate the next block. So afterwards in the cache, let's see. So we're going to load up this whole first block here. We get our block size we're using is capital B. So there's n over b blocks total. What we're going to do is we're going to go through the rows, and each row of 8 we're good with. It's been loaded up already when we're going through the rows. And we've got b squared of these elements, so b squared over 8 misses to get these. And then over here, let's see, what are we doing? So we get 2n Oh, we're assuming that 3 blocks fit into the cache. Okay. So 3 blocks fit into the cache. So that's enough. That's enough for the block from C, the block from B, and the block A, and the block from B. That's good. So let's see. So over here, we are doing 2n over b times b squared over 8. See, so b squared over 8 is loading up all of the lines like before, and then the 2n over b would be that's the number of blocks we have. Right, yeah. So b squared over 8 is the number of misses we need to load up one block, right? Because there's b squared things in it and it loads up in lines of 8. And then we get everything in that line. We use it. And then we have there's n over b blocks per row or column, and then we have 1 row and 1 column, so that's 2n over b blocks that we're loading up. B squared over 8 misses per block is n over b over 4. N times b over 4 misses to calculate one block. And this is going to be the same for all of them. So then we check how many blocks we do total. That's n over b squared. And this comes out to n cubed divided by 4b. And so then we can play around with different sizes of b and see that this is actually going to be better in terms of cache performance. So does this make sense to everyone? This is the number of blocks we have to calculate this cell, the number of misses for each of those blocks. And then that's the total misses. Number of blocks times that amount. Make sense? Okay. So, it's about locality. Matrix multiplications exhibits locality. So, by taking advantage of that locality and doing the multiplications of the things that we already have in our cache before we throw them away and then come back to them later, we end up with better performance. And there's a more detailed discussion of blocking on our website that goes with the book. But of course, this had, it mattered that we wrote the program well. This isn't something that we got for free. We didn't get this more efficient way of doing it unless we actually thought about cache performance when we wrote the program. So, for part B, you'll get, particular cache specified here. And you have these 3 different sizes of matrices that you have to transpose. You should, go through the same, reasoning of figuring out how the best way to, traverse these matrices are so that you, block them up, whatever other strategies you have to get good cache performance. Watch out for warnings when you're compiling your code. They're treated as errors. Think about the eviction policy of the cache. That matters. It's least recently used. You'll have strict compilation flags on. That's why warnings are errors. That's the way we're going to compile it. So, make sure you code with good style, because if you won't, the compiler might actually not let you compile it. Let's see. Yeah, here's, man through get opt. Showed you that already. Eviction policies of cache. So these slides will be online. I know we're over time. These slides will be online, but you should know that the first row of matrix A is going to evict the first row of matrix B. They conflict with each other. They're going to, they have the same set and tag. So they're going to overwrite each other, so you need to worry about, accessing them in an order so that you don't overwrite things more than you have to. Matrices are stored in row major order, so all the elements of a row are consecutive, and then the next row, and then the next row. Read the style guideline. Any questions? Yes?
I use getline at record. For some reason, the Shark machine is an older version of G-C and it requires us to define the GNU source at the top of our file. Is that acceptable, or should we just use fgats instead?
What would you be using this for?
Just to read out to grab lines from the input file.
Grab lines from the input file. You should be able to just do that with, I think we had it over here. I don't know if you need either of those. Just sort of this pattern.
Okay. I have to work with that, but I can adapt it.
Yeah. I mean, if, the source would be, if you submit it to Autolab and Autolab complains about it, then whatever you did is not good.
All right.
That, that's sort of the most definitive way of knowing.